Hello, everyone. Welcome to the first lecture of our quantum mechanics course. Today, we are going to explore the emergence of quantum mechanics. In this lecture, we will look back at the late 19th and early 20th centuries. Classical physics, based on Newton's laws and Maxwell's equations, described motion, forces, and electromagnetism successfully. However, certain experimental observations could not be explained by classical physics, leading to the birth of quantum mechanics. In this lecture series, I will cover 4 key examples that illustrate the foundations of quantum mechanics: blackbody radiation, the photoelectric effect, the Compton effect, and Bohr's model of the hydrogen atom. Let's begin with our first topic, blackbody radiation. To understand this, we first need to define what a blackbody is. An idealized blackbody is a physical object that absorbs 100% of all incident electromagnetic radiation, reflecting absolutely nothing. A great physical realization of this is a cavity with a small hole. Any light entering the hole gets trapped inside, undergoing multiple reflections and being completely absorbed. Now, when this blackbody is in thermal equilibrium at a specific temperature T, the energy absorbed must equal the energy emitted. E absorbed equals E emit. The radiation emitted under these conditions is what we call blackbody radiation. The intensity of radiation is represented by this graph, which shows a peak and approaches zero at both low and high wavelengths. They discovered empirical laws based on experimental observations. As you can see from the spectrum graph on the slide, as the temperature increases, the total radiated energy grows rapidly, and the peak intensity shifts toward shorter wavelengths. This behavior is captured by 2 major classical empirical laws. First, Wien's displacement law states that the wavelength of maximum intensity, lambda max, is inversely proportional to the absolute temperature T. Second, the Stefan-Boltzmann law states that the total power P radiated from an area A is directly proportional to the 4th power of the temperature, T to the 4th. While these laws perfectly described the experimental data, classical thermodynamics couldn't explain why the spectrum took this specific shape. To solve this riddle, Lord Rayleigh and James Jeans attempted a classical approach known as the Rayleigh-Jeans model. They modeled the blackbody as a cubic cavity with conducting walls of length L. Inside this cavity, electromagnetic waves form standing waves. Because the walls are conducting, the electric field must vanish at the boundaries, E equals 0 at the surfaces. To calculate the total energy density, we need to find 2 things. First, the density of states, which is the number of standing waves per unit volume. And second, the average energy per wave. Multiplying these 2 will give us the average energy density of the radiation. Let's examine the mathematics behind standing waves. The given boundary conditions specify that the electric field vanishes at the boundaries. For instance, at x equals 0 and x equals L, the electric field should be 0. The same logic applies to the y and z directions accordingly. Considering that the electric field is 0 at the 0 position, it must be represented by sign functions. Here, kx, ky, kz represent wave numbers of x, y, z directions. To accurately describe the field, we need to sum over all possible wave modes. If we apply the boundary conditions at L positions to the electric field wave function, the wave numbers in the x, y, and z directions must be quantized as kx equals nx pi over L, ky equals ny pi over L, and kz equals nz pi over L, where the n values should be positive integers, because sign function at negative n value is linearly dependent on sign function at positive n values. To calculate the density of states, let's count the number of states, dn, between n and n plus dn. If we consider these states as points in number space, dn corresponds to the number of points lying within a spherical shell of radius n to n plus dn, especially in the limit of large n. Since nx, ny, and nz must be positive, we only consider 1/8 of the sphere's volume, which gives approximately 1/8 times 4 pi n squared dn. By substituting n with the wave number k, we can rewrite this expression. For electromagnetic waves, the wave number k relates to frequency, nu, by k equals 2 pi nu over c, where c is the speed of light. This leads us to dn approximately equals 4 pi L cubed nu squared over c cubed d nu. Considering the two polarization states of electromagnetic waves, we multiply by 2, resulting in dn equals 8 pi L cubed nu squared over c cubed d nu. Thus, the density of states between nu and nu plus d nu is given by g of nu d nu equals 8 pi nu squared over c cubed d nu. Next, according to classical statistical mechanics and the equipartition theorem, each degree of freedom in thermal equilibrium holds an average energy of 1/2 kBt. Since each standing wave behaves like a one-dimensional harmonic oscillator with both kinetic and potential energy, it has 2 degrees of freedom. Therefore, the average energy per wave is exactly kBt. Multiplying the density of states by this average energy leads us to the Rayleigh-Jeans radiation law. U of nu comma t d nu equals 8 pi nu squared over c cubed times kBt d nu. To express this in terms of wavelength, we substitute nu equals c over lambda, which gives negative 8 pi c cubed kBt d nu over lambda to the 4th d lambda. Here, the minus sign arises simply from the order of integration. In the wavelength domain, as lambda approaches 0, that is, in the ultraviolet region, the energy density diverges towards infinity. This dramatic failure of classical physics is famously known as the ultraviolet catastrophe. Consequently, the total emitted energy also diverges to infinity, highlighting the limitations of the classical approach. In the next class, we will explore Planck's quantum model of blackbody radiation. Thanks for watching.